Vector functions, nothing special about these. We have seen vector functions already, but this is just formalizing what we know or generalizing. And this is where the statistician and the mathematician again think differently. To me, vectors are points in space, extended to n dimensions and whatnot. When I use results from mathematics, they are still points in space. But mathematicians look at points in space as functions of some kind. Now, sometimes they are easy, sometimes not so much. Now, why do we need to know about vector equation, vector functions? I'm going to look at this already, I believe, when we talked about 3 dimensions the very first time, I guess. In the XY plane, typical calculus 1, in order for something to be a function, it has to pass the
Vertical line test.
vertical line test. Great. So, function, great. Okay. If we have something, we have an equation. Yes. If I drew a line, y equals mx plus b, a parabola, a times x minus h squared plus k, vertex, and you know the direction. Sine is a function, cosine function, tangent function. All of those are functions. If we have a function, we have an equation, great. Things are in. When something is not a function, really bad artistry, what do we do? Abort mission. Isabella, what do we do? Not that. Here. You don't know.
Well, there could be a situation where you can write it as one equation in terms of x and y.
Okay, there could be a situation
But-
where you write it in terms of one equation. What is that equation?
Well, assuming this is a unit circle, we can write that as x squared plus y squared equals 1,
Okay, if I generalize it to any radius,
r squared.
okay. X squared plus y squared equals r squared. Calculus 1, we would rewrite this in terms of just x, y equals something, graph it. Otherwise, the calculator will not graph it because won't pass the vertical line test. This is fine. What is another way? Parametric equation, right? So, or cosine t, or sine t, yes. And then depending on polar coordinates, cylindrical coordinates, whatever, we would have theta here, right, to represent angle. One and the same. End of the day, it goes to that one guy named Pythagoras, right? So a vector in 2-dimensional space, x, y, I can simply write it as a parametric form x of t and y of t. Agreed? And for a circle, these 2 points or that vector is simply r cosine t, comma r sine t. Agree? Well, r is the radius of the circle, and as I change the value of t, it is going to trace the circle out. Do we agree? So, In pre-calculus, the direction matters, and whether you go in clockwise direction or anti-clockwise direction, we use angles differently. Why so? Well, in practice, that's how things are done. Aviation, marine stuff, angles are defined both in terms of positive and negative angles. So typically speaking, what direction do we use?
Counterclockwise.
Counterclockwise. So from here. Good. So T is going to trace this curve, starting here and ending there. Agree? Great. Now that we see the purpose of a parametric equation in 2D. Okay. Could I call each of those as parametric functions? Yes. This entire form represents a vector. Agree? Yes. Hence we call them vector functions in 2D. I simply want to extend this idea over there so that I can trace something out in 3 dimensions. Any thoughts as to how I can do that? Simply add a component, right? Since day one, my idea here was to start with 1 dimension, explain it in 2 dimensions, something that you are used to, and just say, add another component. It'll apply to 3 dimensions, n dimensions, and whatever, infinite dimensions. So x of t, y of t, z of t. Good, that's it. Vector function, 3 dimensions. One may say, why a parametric form? Can't we just simply live happily ever after with an equation such as a sphere? I could do x squared plus y squared plus z squared equals r squared. Life is great. Correct. Why not? Why not be content with just an equation in 3D space time?
This is because, like, depending on how the function ends up, things are gonna stack up, or it's not gonna be like.
It's not going to be one-to-one. In other words, I love bees. 1, bees loving hippie. 2, bees are cute. 3, they've never have stung me before in my life. Hopefully they don't. They share the love. Hopefully it's mutual. Now imagine a bee that's going from flower to flower and starts here. And that is the part of that bee. It is doing all that stuff and ends at its hive. Good. And I want you to represent that part using a function. No, right? Not possible, because whatever we learned about functions is not going to apply here, because not one-to-one. You know, it's going all over the place. Even in terms of vector functions, this is hard, which is why I started with a line segment. So from here to here, I'm going to represent its path, there to there. That's going to be hard, maybe from there to there to there. Really hard. But if I use functions on those pieces, I can trace out the path of this peak. Agree? So if I want to extend things directly to 3 dimensions, sphere, easy. Nice little path. Cylinder, easy. Right, cube, very easy. A path like this, not so easy, right? So the generalization is to use the vector function. Good. once we identify the functions though, if and when they are possible, whatever we do with functions will also extend to vector functions. Okay, calculus 1. What is a fundamental thing that you learned in calculus 1 when we first started calculus 1? Vector value functions, vector functions, say FGH. Now, in calculus 1, the first thing that you did was limit. Limit is simply the value a function approaches for, or as x approaches a value a or c on the x-axis. Why are limits important? We want to know if, especially for example, a function that has a horizontal asymptote, what is that value in the long run? Is it going to converge to something, or is it just going to blow up into something else? Often used in theoretical analysis, but we had a very specific application in calculus 1. What is that application of limits?
The definition of the derivative.
Definition of the derivative, Caleb.
I was gonna say the summation of limits.
Summation of limits.
I think it's something else.
Okay, and
I mean, it's the end of calc 1. The integral.
Are you referring to integral?
Oh, it's like,
So I'm still at the beginning of calc 1. So at the very end of calc 1, integrals, and when you sum a bunch of rectangles, take the limit, you want to know if you put infinite rectangles under the curve, then what is the actual area? Now, in practice, is it ever possible to do infinite rectangles? No. In a theoretical sense, we come up with approximations, which is why there is no such thing as perfection. You can get almost perfect about something, but never perfect. It can only happen in limits, and good luck with that. Philosophy with calc 3. Moving on. So the purpose of limits is to find derivatives as an application. And then we have integrals, yes. Now going back to derivatives, extended one step further, but this time as an application, not in math. Again, do keep in mind, derivatives are an application, right? Tell you a question.
No.
No?
Sorry, I was like the rate of change of something.
Hold that thought for a second. She read my mind. So as an application in physics, engineering, chemistry, whatnot, a scientific application, what is the purpose of a derivative? What she said, right? Rate of change. Now, in terms of rate of change, we have two types. What are the two types?
we're talking physics terms.
Sure.
I mean, I guess it's like acceleration.
Oh, no, that is the application after what I'm asking. So after this initial step. You're going with okay, physics. Now, Talia actually gave you a hint. Rate of change. All I need for you to is fill in the blank before rate of change.
Positive or negative.
Okay, fine, but no.
Word game.
Okay, so it's word game. First option starts with the letter A, ends with the letter E. Oh, damn, E. I was counting in my head. So 7-letter word, right?
As of that, then rate of change,
What?
or average rate of change.
Average rate of change, right? Okay. Do we need working?
Instantaneous.
Okay, good. Save me from the trouble.
Yeah, I don't want to calculate the lessons.
5, 10, 12 letters, right? Instantaneous rate of change. What is the difference between average and instantaneous? Average over an interval, instantaneous at a particular point. Of the two, which is effective?
Instantaneous.
They both are. In what way, Colin?
Depends.
Depends on what?
What you're doing, I mean, probably in this case, average.
Based on like a shadow track.
So if I happen to be, it's average.
I mean, it depends on literally what you wanna know. If you wanna know where the B is, it's.
Okay. Now, I'll tell you that in the case of the B, instantaneous is the most accurate way, not average. So. Not really, but a line, right? Let's just say this is y equals to x plus 2. Good. The line is growing, agree, as x changes, y changes, and positive, negative rate of change. Since it is growing, the rate of change is positive. And what is that amount? 2. Now, it really doesn't matter where I am. Let's say this is time, and things are growing with respect to time t, and the function f of t is simply this. And as things, time is changing, the growth is linear. Does it matter at what time point I'm in? The rate of change doesn't change, no matter what time point you're at. So here, from here to there, I can just do the average and move on. Agree? Could I do the instantaneous? Absolutely. But nah, for that case, not me. I'll take a realistic example for the instantaneous one. Let's say bank account, savings account, retirement, whatever. It is going in that manner. No one here is a finance major. Right? In finance, or someday you might buy a house if things change. You can forget about Florida, especially this area, unless you're wealthy. So, really wealthy. Hypothetically, things change, you're buying a house in this area, and you are getting a mortgage, right? You pay some initial amount and say there is an interest. You are saying how things would happen in 30 something years, typically. Is that mortgage going to grow the loan that you purchased over time? Technically, yes, your principal will increase in 30 years. You are going to end up paying more, even though any bank will give you what's called an amortization schedule, which tells you how the payments will change your amount. But at the end of the day, you will be paying more if you wait for 30 years. Yeah. If you're going to die anyway, it doesn't matter. It doesn't. So just put it for 30 years. In the long run, it doesn't matter because you'd be dead.
Philosophy with calculus.
Huh?
I said philosophy with calculus.
Exactly.
Doesn't matter.
Let's do it practice. So
And tax law.
perfectly fine, right? Unless you plan on living forever, you know, at an average age of 35, you want to buy a house, doesn't matter. Just pay that mortgage payments and get the interest. it's perfectly fine. But the point I'm trying to make is it is going to grow rapidly. So the rate of change that you have at each time point is not going to be the same. Now, this is a true exponential. In finance, there is a formula, you have to rewrite everything, and that formula would be in terms of R, the rate, N, and a bunch of other terms. But it is related to an exponential. We lived through COVID, we started with one person, things blew up in an exponential manner. So the rate of change at each time point wasn't the same. In this case, if I took the average from here to there and found the rate of change, is it accurate?
Accurate to what?
Is it an accurate representation of how things changed or the growth rate?
Depends on the distance between the 2 points.
It depends on the distance between the 2 points. I consider that to be pretty far away. Rachel, did you say something?
Well, yeah, it represents that time frame, a whole graph.
Okay. Given the choice between an average and instantaneous, what would you go for?
Instantaneous.
Instantaneous if you are particular about accuracy. If you don't care about accuracy and you just want a quick conclusion, this, right? So instantaneous will give you accuracy over here. Something like that, good. And I want you to find the rate of change. So you start here and go up there and you drew a line and came up with the rate of change. Is that accurate? No, it is not accurate at all because you are missing bits of information on how things changed. It wasn't steady, it went up, it went down, went back up. So using an average rate of change here, it's no good. So I mentioned earlier, aviation, marine stuff, they use hundreds, right? Plane moves here and there. We've gone to space. Could I be as flexible as I am there when I'm putting people in a shuttle and sending them off to space?
Okay.
I mean, if you want to pay your mortgage really fast, sure.
I mean, we did it in the 60s.
Put them in a shuttle, calculate average stuff and fly them out. You don't have to worry about your mortgage. End of story, right? You will be risking lives and all kinds of stuff. Caleb, did you say something?
Yeah, so we did it in the 60s, I mean.
Yeah, they did it properly too, right?
True.
And we have made improvements to a point where right now people are talking about quantum computing and stuff. So we need precision, extreme precision in physics, period. So we can't rely on this. We need instantaneous rate of change. Same with engineering. You need to know, you need to have precision. People rely on engineers to build bridges properly, a building properly. So,
Oh, engineers make the plans, the actual workers are the ones who build it.
true, but if you want to draw the plans and suggest materials, you need to know the length of the beam, you need to know how much force it can handle. I can't approximate things there. Precision matters. You will learn the different types of beams, you know, V, W, L shape, U shape. I was required to take Introduction to Civil Engineering in my bachelor's for electrical engineering. It was a prerequisite. So I've made the point as to why instantaneous rate of change matters. So when we find the derivative, we are finding the instantaneous rate of change. But in order to find the instantaneous rate of change, we use the average rate of change, correct? And that part had a name. In calculus 1,
Difference question.
difference quotient. Do we like Dairy Queen?
Yeah.
No, yeah. I just like sweet stuff, so leave you. Next time you go to Dairy Queen, think of difference quotient. So for a function, the difference quotient is simply, I'm going to write it in terms of t because we can relate it back there. F of t plus h minus f of t divided by h. By all means, this formula is the slope between 2 points. If you have a function f of t and you find the slope of f of t on t in t to t plus h, 2 points. You start at t and at t plus h. The formula for slope is y2 minus y1 divided by x2 minus x1. Y2 simply is the value of the function evaluated at t plus h, yes. Y1, that's value of the function evaluated at t. X2 minus x1, t plus h, minus t, I simply have h. So pretty much we're using the slope, but that is the average rate of change because we are over an interval. If I want to find the instantaneous rate of change, we apply the limit h approaching 0. I have students in calculus 1 ask me, well, why can't I simply put h to be 0? Well, 1, denominator will become 0. And 2, in a practical sense, if h is 0, you're going nowhere. You're just at t, right? What is the point? So when we say h is approaching 0, we're not saying h is equal to 0. Hopefully you know that by now. So if I took the limit of the average rate of change, I am going to get the derivative at t, which in and of itself is a function. That is the instantaneous rate of change. I consider myself to be a derivative because I rock. That's a good joke. That's good. Okay, now, if you have to explain derivative to someone in the simplest terms possible, how would you explain other than calling it as instantaneous rate of change? Tell me.
By the slope of the tangent line in specific point.
Okay, slope of the tangent line in a specific point, and that is the simplest way.
I mean, when I picture in my head, I mean, for this,
Okay, let's say you're going to explain it to someone who doesn't know a lot about it.
Had to do this a few times, so I would explain derivatives mainly as position versus velocity would be a derivative, and velocity versus acceleration would be a derivative.
A person who doesn't know math that much would not know what derivative is.
Or someone who drives a car would know.
No, they would know velocity and acceleration. They wouldn't know what derivative of the function is.
I know, I thought that's what I was trying to represent.
No, in simplest terms, you have to explain instantaneous rate of change.
It's just how quickly something's changing at a given point in time.
Come again?
It's how quickly something's changing at a given point in time.
Well, that would be confusing to me, right? Because if I'm standing at a point, going back to Caleb, who associate it to the velocity and acceleration part, I completely agree. But what does derivative, or how does it relate to those two? And if you said, oh, how things change at a point, well, at a single point, how is your velocity changing? It's not changing at all, right? Yes? Your hand went up.
The way I always describe it to people is I say, imagine you're driving a car
Imagine driving a car,
and
okay.
you're on I-75
Perfectly fine, I didn't say you were wrong, Caleb.
and you're driving your car from, from Fort Myers to Tampa, and you can look at your average speed throughout the entire trip, or you can look at how your speedometer changes at every second you're driving. And the change in your speedometer, the value of your speedometer at every second is the instantaneous rate of change, which is a derivative.
Good. So I hope you don't do this when you're driving from here to Tampa. One, you might get a ticket. Two, you might end up paying your mortgage really fast. So every second, if you measure that speed, then you will know that instantaneous. The key word that Chris used is every second, right? That is pretty close to the time point, right? It is not an instant, but it is close enough. Yes, if I extend the second to millisecond, I actually got closer. Yes, in terms of instant. Millisecond to microsecond, extremely closer. Micro to nano, getting very, very close. But if I go from second, millisecond, microsecond, nanosecond, time is getting smaller and smaller and smaller. In other words, h is approaching 0. Good. So, again, it is theoretical. We are simply going to extend that concept that we used in 2 dimension, 1 dimension, 2 dimension, over to 3 dimensions. If you have a vector valued function or a vector function, I'll call it R of t because we've been using this for a while. And if I wanted to know the limit of that function, t approaches c, R of t, we will have the derivative, yes. All we are going to do, distribute that limit through, that is all. So it goes back to properties of limits. If you have 2 functions that are added together, then I can apply the limit for the first function, apply the limit to the second function, add the limits together, agree? But here, we're not adding them, we're just applying them for each of the functions separately and leaving it as is, or leaving them as is. So I can write this as limit x approaches t approaches c f of t. T approaches c g of t. T approaching c h of t. Great. Distributing the limits, and that is all. Go ahead.
Isn't that gonna be a value? Like, isn't that going to be a specific point if it's approaching a constant?
No, all we are saying is if I take a limit for the x coordinate over time, it will approach this one point in space. In space, in 3 dimensions, it is going to approach this one point in space. We are not talking about a function in general, rather we are referring to the component functions in 3D space. So each of these functions correspond to a component in the vector. Do we agree? So all I'm referring to is where this point for a plane or for a function will end up in as t approaches c or t approaches infinity. So let's say, okay, think about it this way. Let's take a trajectory in some space shuttle or, a flight of some kind, a plane of some kind that you have. And you started somewhere, you are following some sort of an arbitrary trajectory, and you somehow broke the barriers and you are way in space, and based on the trajectory that you're taking, if someone asked in that number of light years, where will this particular shuttle end up at? You're not going to give them a function. You're not going to give them a single value. You are going to give them a point in space. That point perhaps is some point on a rock in some galaxy, who knows? But based on all your calculations, you're simply saying, as t approaches some value, this is where the shuttle will be. Good? So, go ahead.
So that's not a derivative. It's just a,
We haven't gotten there.
okay, that's why I was,
Okay, maybe I'll take it off. Thank you. That's not you are making a good point. This is simply, I got one step ahead. So this is simply referring to where in space you would end up in as, let's say, time t approaches c. Now, c could be any number. It could be positive infinity, negative infinity, and do get rid of the derivative part. We haven't gotten there yet. Good. So no need to add, subtract, divide. We are simply distributing the limits through. Start with the simple case. Now we all understand as to why we need parametric functions. Agree? Okay. If I want to know how things change, first 2D, we can extend it to 3D. Next time, we're running out of time. Not bad. It is bad. Okay. We know I can trace that circle out. Do we agree? Yes. We know the parametric equation, cosine t, sine t. Yes. Okay. If someone asks you, well, how are things changing right at that point if I start here and head in that direction? Important question to ask. Yes, especially in physics. Well, at that instant, how do things change? Talia actually gave the answer. She was explaining it to me, not to a person who didn't know mathematics that well. But she gave the answer. So how do I find at that instant? Just a tangent line? Slope of that tangent line. So if I find the slope of the tangent line, that simply is the instantaneous rate of change. In other words, the derivative at that point. Well, what is a tangent line? That isn't, don't tell me it's a line. We know that.
A line that is king.
oh,
Oh.
A line that intersects a function of 1 point.
A line that touches or intersects a function exactly at 1 point. very hard to draw here, but I'm gonna try. Good. Just touches at that one point. Does that give me direction? Well, now if I'm going this way, it is decreasing, yes? I've got to flip the slope, right? Because I'm going that way. So that is a part that we can deal with later. But this tangent line, as I move, it is going to change, yes? Up, there it's flat, meaning no change, down. Again, the sine part, we will deal with that in, when we get to it. So we want to find the equation of the tangent line. The equation of the line at that point, it is going to depend on cosine and sine. Yes? Now do we get as to why we call it tangent? Sine, cosine. We don't call it tangent because the gentleman went and got a tan. Sine over cosine is tangent. So one of many reasons as to why we call a tangent line, because angles and sine, cosine. So if I find the derivative, then I will know the instantaneous rate of change. And into the case, I am going to stop here for now, but I will give the explanation as to why this is true. I simply have to find the derivative of the first component, derivative of the second component after making an adjustment, because I have to include the rate of change between points. Yes, that part we will save for next time.